Hello dear students, I hope you are all doing well and welcome back to your physics class. Today's lesson, we are continuing to explain about the magnetic force. So in a previous lesson, if you remember, we studied the magnetic force on a charged particle. For example, when a charged particle is moving in a uniform magnetic field, this magnetic field experiences a magnetic force on a charged particle. So the charged particle in a uniform magnetic field experiences a magnetic force. So the amount of the magnetic force on a charged particle that produced by the magnetic field depends on the amount of charge, the velocity of charge, the magnetic field, and the angle between V and B. And also we studied when does the magnetic force on a charged particle become zero, even if the particle is moving in a uniform magnetic field in two angles. When the charge's movement is parallel to the magnetic field, like parallel by 0 degree and parallel by 180 degree, in this case, no magnetic force experiences by the magnetic field because sine 0 is 0 and sine 180 is also 0. We stop it here in the last lesson. The charge's path, we have two charge's path when the charged particle experiences a magnetic force by a magnetic field, circular path and helical path. So when does the charged path become a circular path and when does the charged path become helical path? And when does no force acting on a charged particle? Now I will explain one by one in detail. Guys, look. Magnetic force becomes maximum value when does magnetic force become maximum value? If the angle between V and B is 90 degrees or when V and B is perpendicular to each other. When a charged particle enters or encounters a uniform magnetic field perpendicularly, in that case, the magnetic force reaches maximum value. So, when does magnetic force becomes maximum value? When angle is 90 or 270, or you can say when V is perpendicular to the magnetic field. When V is perpendicular to the magnetic field, the amount of magnetic force becomes what? Becomes maximum value. So what about the charge's path? The charge's path becomes what? It becomes a circular path. Okay? So let me ask you a question. When does charge's path become a circular path? When a charged particle enters or moving perpendicular to the direction of the magnetic field. Like for example, when the magnetic field is directed into the page, what do you mean by this cross? Cross indicates the direction of the magnetic field. Cross, it means into the page. Magnetic field is into the page. Into the page. Look, when the magnetic field is into the page, and for example, when the charge is moving in this direction, okay, the movement of the charge is perpendicular to the direction of the magnetic field. According to right-hand rule, the positive charge, so the positive charge when V is in this direction perpendicular to the magnetic field, according to right-hand rule, V is the thumb is represented for the direction of the V, okay, the velocity of the charge. And the four fingers is direction of the magnetic field. We have two forces, guys. Positive force out of palm and negative force, your palm, according to your right-hand rule. Here we have positive. So the positive charge, it should be moved in a circular path. Look. And it moves counterclockwise. When does the charge's path become a circular path? When the charge's speed is perpendicular to the magnetic field. Okay, in the second case, when the magnetic force decreases or between maximum and minimum value, if the angle between V and B more than 0 or less than 90. Between this angle, more than 0, the magnetic force increases. Less than 90, the magnetic force decreases gradually. So the charge's path becomes helical path. Becomes what? Helical path. When does the charge's path becomes helical path? When the charge's velocity is makes angle with the magnetic field, or when the charge's particle enters the magnetic field in a tilted angle, not in right angle or not perpendicular. How? Look, assume that this is magnetic field. The magnetic field is directed to the right. This is magnetic field. If the positive charge or negative charge, it doesn't matter, no problem, okay? When the charge's particle enters the magnetic field, okay, in a tilted angle, is the direction of the speed perpendicular to the direction of the magnetic field? No. Angle between V and B is 90 degrees? No. So, can we say this is perpendicular? No, this is not perpendicular. In the case when the charge's speed is not perpendicular to the magnetic field, the charge's path becomes what? Becomes helical path. Becomes what? Helical path. The magnetic field produces the magnetic force, or exerts a magnetic force on a charged particle, but it is path, the path of the charge becomes helical path, not circular path. When does, at which of the following angles, the charge's path becomes helical path? Angle 90? No. Angle 0? No. Angle 180? No. Angle 60? Yes. More than 0, less than 90? Yes. The charge's path becomes helical path. So, when does magnetic force become zero? Becomes zero, guys. Magnetic force, it becomes zero even if the charge is moving in the magnetic field when angle 0 between V and B, or when angle is 180 between V and B. So can we say when V is parallel to B? Yes. So we have two angles of parallel. Parallel by 0 degree, parallel by 180 degree. As you can see in this picture, guys, look, if you have a positive charge and the positive charge is moving in the same direction of the magnetic field, what is the angle between V and B? Angle between V and B is what? 0. When angle is 0, the magnetic force becomes what? Becomes 0 also. Why? Because the sign 0 is 0. And the charge's path doesn't change. No magnetic force exerting on the charged particle. The magnetic field does not exert the force on a charged particle, even if the particle is moving. So, can we say the particle is continues moving on a straight path? Yes. There is no force acting on the charged particle to moving upward or moving downward to make a circular path or helical path. There is no magnetic force when V is parallel to the B. When does active magnetic force on a moving charge becomes half of its maximum value? When does the magnetic force becomes half of its maximum value? You can find angle sine inverse of what? Sine inverse half of its maximum value. Sine inverse half is equal to 30. Okay? So when does when does the magnetic force becomes quarter of its maximum value? Sine inverse of quarter is equal to something by calculator. When does the magnitude of magnetic force becomes like one third of its maximum value? Theta is equal to sine inverse 1/3 of its maximum value is equal to something. Okay? What happens if the charged particle moves perpendicular to the magnetic field? What happens to the charged particle when it moves perpendicular to the magnetic field? As I explained it for you, as I mentioned, when the charged particle is perpendicular to the magnetic field, the charge's path becomes a circular path. Okay? So for every circular path, we have centripetal acceleration. When an object is moving in a circular path, even if the particle is moving in a circular path, in every circular path, there will be a centripetal force. The centripetal force for the charged particle, when the magnetic field exerts a force on a charged particle, when a charged particle is moving perpendicular to the magnetic field, this charge is moving in a circular path. Okay? So, the circular motion provided by what? By the magnetic force. The centripetal force provided by what? By a magnetic force. The magnetic force acts on a moving charged particle, and the particle moves in a circular path. In what? In a circular path. A force that maintains circular path changes only the direction of the V node. It is magnetic. When the charged particle is moving in a circular path, okay, it experiences a magnetic force. This magnetic force, the magnetic force, it goes to moving the particle in a circular path, okay, and the centripetal force provided by what? By magnetic force. This centripetal force provided by what? By a magnetic force. Look. So, centripetal force, in chapter 1 we studied, guys, mv square over r is equal to what? qvb. V with V cancel. What is remain? mv over r is equal to qb. So, we have 5 variables to find B. Like, for example, if the question asks us to find the magnitude of the magnetic field, is equal to mv over qr. mv over qr. Guys, look at question 10. 2 charged particles are projected into a region where there is a magnetic field perpendicular to their velocities. When the magnetic field is perpendicular to the velocities, when B is perpendicular to the V, the charges path becomes a circular path, and like how many charged particles do we have? We have 2 charged particles. 1, 2. This 2 charged particle entered perpendicular to the magnetic field. Assume that the magnetic field is into the page. Assume that the magnetic field is into the page. Guys, how many particles do we have? We have 2 particles. But I don't know which particle is positive and which particle is negative. So the question says, if the particles are deflected in opposite direction, if the 2 particles are deflected in opposite direction, what can you say about them? When does these 2 particles are deflecting in opposite direction? Or when does these 2 particles deflect in opposite direction? When the 2 particles are in opposite charge. When 2 opposite charges particle enters this magnetic field, they deflect in opposite direction. Like, for example, if the charged particle enters, this is your thumb is direction of V, V to the east, okay, V to the east, and B into the page. Out of palm becomes positive charge. Your palm is negative. So the positive charge moving upward and the negative charge moving downward. Look, this one becomes like this. This is positive charge, and the negative charge it moves down, and so we can say these 2 charges must be in opposite charge, must be opposite charges. Why? Because only 2 opposite charges deflect in opposite direction. If the 2 charges, like they have the same charge, the 2 charge deflect in the same direction. But because the question mentioned both of them deflect in opposite direction, they have opposite charge. They must have what? Opposite charges. Question 11, very good question, guys. Suppose an electron is chasing a proton. Electron chasing a proton. This is electron, negative charge, and this is proton. Up to this page, it means moves upward. Okay, V. Both charges, positive and negative charges, moving upward, moving up to this page. When suddenly magnetic field pointing into the page. Suddenly magnetic field pointing what? Into the page. The 2 charges, electron is chasing a proton up to this page. It means that both electron and proton moving upward. Okay? What would happen to the particles? What would happen to the particles? According right-hand rule, the thumb is represent for the direction of the velocity of the charge, the speed of the charge, the movement of charge, and B is into the page mentioned in the question. Your palm deflect is in this direction to the right. The electron, the negative charge deflect to the right, and the positive charge deflect to the right according right hand rule. Okay, this becomes negative charge. The negative charge deflect to the left, and the positive charge deflect to the right. The answer, the proton will go left and the electron will go right. Electron right. Sorry, this side is right, and proton left. Electron will go to the right and proton to the left according right hand rule. Very best friend. We have two friends, positive friend in your palm, out of your palm, and negative friend in your palm. V, the speed of charged particle. The four fingers represent for the direction of the magnetic field. How many forces do we have? Two. Force of exerted on a positive charge and force on a negative charge. The the angle between magnetic force and B always perpendicular. Angle between force and V always 90 perpendicular. Force is always perpendicular to both of magnetic field and V. Only the angle between V and B changes. Okay? Angle between V and B changes. Can a stationary magnetic field set a resting electron in motion? Set a resting electron. What do you mean by resting electron? Resting electron, speed of electron is 0. Can a stationary magnetic field exert a force on a resting electron? No. There will be no magnetic force, guys. Why? Because magnetic force depends on the speed. If speed is 0, magnetic force also 0. No, because magnetic field only exerts a net force on a moving charge, not the stationary charge. For stationary charge, we don't have magnetic force, even if we have a magnetic field. Why does the picture on a television screen become, this is question 12, become destroyed when a magnet is brought near the screen? When you brought the magnetism near the screen of the TV or a smart board, like, for example, the picture on the TV becomes destroyed. Why? Because when you oppose the magnetic field near the surface of the screen, this magnetic field exerts a magnetic force on a charged particle when it's moving on the surface of the screen. Because the picture produced by the cathode inside the TV, inside the screen, so this cathode projected many electrons to the surface of the screen, and at the surface of the screen there is a lot of movement of electrons. So this movement electrons will be like the force exerted on the TV by the magnetic field. Why? Because the magnetic field can exert a force on a moving charged particle. Because the magnetic field of a magnet exerts a force on the moving electrons in the electron beam. About the circular path of a charge moving through the field. Guys, these two notes are very, very important. Be careful. Look. Now I'm going to write a very important note about the charge's path when magnetic field into the page or when magnetic field out of the page. If magnetic field is into the page, when magnetic field Z negative. What do you mean by into the page? Z negative. Positive proton becomes counterclockwise. Counterclock. And electron clockwise. In the second case, but when magnetic field is out of the page, Z positive. When the magnetic field is out of the page, proton, positive charge, moves clockwise direction. and electron moves counterclockwise direction. So this note is very important, guys. Once again, listen carefully. When the magnetic field is into the page, when magnetic field is directed into the page, Z negative, proton, positive charge, will move in counterclockwise direction. But electron, it moves in clockwise direction. Let me ask you a question. When does the positive charge move counterclockwise? In which of the following? When magnetic field out of the page? No. When magnetic field directed into the page, Z negative? Yes. When does electron moves clockwise? When magnetic field into the page. But if the magnetic field is out of the page, proton, positive charge moves clockwise and electron moves counterclockwise. Okay? Now I'm going to prove by now I'm going to make a figure. Assume that this is magnetic field, guys. What is this? This is magnetic field. How positive charge moves in this magnetic field when the charged particle is perpendicular? When the charged particle is perpendicular, for the positive charge, because this is into the page, like for example, if the V is entered like this, in this direction, okay? Out of palm is positive. Positive is what? Counterclockwise. Positive becomes what? Counterclockwise. When does the positive charge becomes counterclockwise? When field is into the page. When field is into the page. Positive, proton, counterclockwise, yes. What about electron? Electron, it moves clockwise. Look, electron is what? In clockwise direction. But electron, clockwise direction. When does the charge electron's path becomes clockwise direction? When the magnetic field is directed into the page. When magnetic field is into the page. When magnetic field is into the page, electron moves clockwise direction. Electron moves clockwise direction. Okay? If the direction of the magnetic field into the page, proton will move in counterclockwise, but electron clockwise. But if the direction of the magnetic field out of the page, proton will move clockwise, while electron moves counterclockwise. Under what condition does the charged particle experience no magnetic force in a magnetic field? In the following situations. Like for the particle is stationary, like for the stationary particle, when magnetic force, if the charged particle is not moving, there is no magnetic force because the velocity vector is 0. When the particle moves parallel, angle 0 and 180. Or when the particle has no charge like neutron. When the neutron is moving perpendicular into the magnetic field, what will be the amount of the magnetic force? There will be no magnetic force. Why? Because magnetic field does not exert a magnetic force on a neutron. Okay? The magnetic field only exerts a magnetic force on a charged particle. Neutral is not charged particle. Has 0 charge. That is why it has no magnetic force. Question 13. A proton moving horizontally enters a region where there is a uniform magnetic field. Horizontally, the proton. What is the charge? Positive charge. We have positive charge. Guys, it is very important to recognize the question. The question is about the electron or proton. Why? Because the direction of the magnetic force is different between the direction of the magnetic force of proton is different from the electron. Okay? So, but for determine the magnitude of the magnetic force, they have the same equation for positive charge and for the negative charge. Because they have the same charge as well. When the proton moving horizontal enters a region where there is a uniform magnetic field perpendicular to the proton's velocity, as shown beside, the figure is given, guys. The figure is given. Look. The proton is moving horizontally and enters a region where there is a uniform magnetic field and the direction of the V and B is perpendicular. B into the page, but V to the east. The direction of V and B is perpendicular. Angle between them is 90. So what is unknown? Describe the proton's subsequent motion. Describe the proton's motion. Guys, according right-hand rule, velocity, field, force of proton, out of palm, force of proton. Guys, put your fingers in the direction of velocity, east, and the four fingers, your thumb is in the direction of V, and fingers direction of B. Where is out of palm? Upward. So, because the charge is positive, so the charge experiences a magnetic force, okay? But the circle does not complete here. Why this circle does not complete? Because there is no field here. There is no magnetic field here. So that is why the charge is moving in a straight path. So the protons will curl in a semicircle, in a half circle. Why this is half circle? This is into the page, it becomes counterclockwise. Because there is no field here. So how would an electron behave under the same circumstance? Electron. What about if we have electron? Electron, V, thumb, V. V is into the page. Electron is out, is your palm. Your palm is the direction of the electron. Is moving. Complete circle or half circle? Half circle. Why? Why half circle? Because there is no magnetic field here. There is no magnetic field here. Magnetic field is 0. Proton would move up in half circle. Electron move down half circle. Okay? Half circle. As you can see in this animation, like, look, guys. Look, we have a charged particle. We have a charged particle. The charged particle is moving. Look, the charged particle is moving horizontally and enters uniform perpendicular. Field is into the page. The charge experiences a magnetic force. It goes to moving in a circle, but this circle is finished here. The particle does not move in one complete circle. Why? Because there is no field here. If we have a field here, the charge's path becomes what? Circular path, complete circle. But this path is a semicircle or half circle. Why? Because only here we have magnetic field. We don't have magnetic field here. This charge must be negative or positive. I don't know what is this charge. But by its movement, I know the type of the charge. According right hand rule, V enters into the magnetic field and the four fingers into the page. Your palm in the direction of electron. So that is why this is electron. This is what? This is electron. Okay, guys. Let's go back to our PDF. Look. At a given instant, a proton moves. Proton. What is the type of charge? Proton. Moves in a positive x. Moves in what? Positive x. This is proton. In positive x direction. In a region where there is a magnetic field in negative z. Magnetic field, negative z. Field, negative z. It means that the direction of the magnetic field is into the page. Direction of the field is what? Into the page. Okay? Field is into the page. What is the direction of the magnetic force? Field is directed to east. Force is upward. The direction of the magnetic force and the charged particle is moving in what? In a circular path. Clockwise or counterclockwise? Counterclockwise. Why? Because field is into the page. But this charge, this magnetic force is acting in XY plane, horizontally. Does a proton continue to move along the X and Y? Only along the X? No. The answer is the positive Y. The direction of the charge is moving upward, positive Y. Direction? No, it doesn't continue to move along the x-axis. It moves in a circle in the xy plane. Because, guys, there is a difference between like in grade 11 we studied that the horizontal path is x and vertical path is y, but here for the 3 dimensions x, y and z, x to y they always located at the same plane, horizontal, but z positive and z negative becomes vertical. At first the charge is moving on a x-axis, so the magnetic force exerted is upward. So this force is moving in the xy plane, not z. It moves in a circle in the xy plane. Guys, that's all for today. Inshallah, in the next lesson, we will solve all questions that related with the right-hand rule in a magnetic force, and all solving questions about the magnetic force to determine the magnitude of magnetic force on a charged particle. Thank you for listening. See you soon as possible, inshallah.